In this video, we're going to return our focus to functions of x and y and just that relationship. So we have x and we have y that dictate the height or the value of some function f. We're not going to have any inputs to those functions. We're still going to get more derivatives though than we had previously, and we'll see how that appears naturally just looking at this relationship here. If we imagine a function is given to us, like x e to the y plus y over x, we'll just remind ourselves that that is y times x to the negative 1, which makes it easier to differentiate. Then the partial derivative of f with respect to x would be e to the y plus, if we take the derivative of this with respect to x, we'll have negative x to the negative 2 times y. And we would tidy that up as e to the y minus y x to the minus 2. We'll leave it in this form for a moment. You'll see why in a second. Similarly, we can go back to the original function and take the y derivative. We're going to get x e to the y plus y x to the minus 1. Oh wait, the y derivative is 1. So we just end up with x to the negative 1. There we are. Now those derivatives that we just took are what we would call first order derivatives. We took one derivative with respect to x and one derivative with respect to y, but it was only one derivative each time relative to the original function. However, we've seen in the past that we can take another derivative, and here we're going to do that again. We're going to have to be a little more specific about which derivative we're taking. Now we're going to take another derivative of this with respect to x, and that's going to give us the second order partial derivative, having worked with the same function, but taking the x derivative and then taking the x derivative of that. We'll do that on the next page, but we'll be starting from this value here, which is the first derivative with respect to x. So we're going to compute this derivative. That's going to be the derivative with respect to x of what we found already. That's a partial derivative there. And that term there is, back a page to check, e to the y minus y x to the negative 2. So now we're going to apply this as a verb. We're going to transform this by taking the x partial derivative. Oh, wait, there's no x's at all in this first term. So in fact, that first term is 0. The next term, the y is a constant, and then the derivative of x is going to give us negative 2x to the negative 3. Overall, that's going to turn to a positive 2y over x cubed. And that is what happens when we take our original function, we differentiate once with respect to x, and then we differentiate again with respect to x. And we actually see an explosion of possibilities here. We can do that same thing, but with different mixing and matching. We could take the y derivative first, and then an x derivative. Let's do that next and see what happens. Keeping in mind the formula we found for the y derivative was x e to the y plus x to the negative 1. X e to the y plus x to the negative 1. And we're taking the x derivative of that. So x is our variable this time. So it's a lot of mental gymnastics switching between constants and variables. Minus x to the minus 2. And we can mix and match the other way if we want, actually. We could take the y derivative last, take the x derivative first. Well, we already had that up here. This partial derivative here is this value, this function. And we take the y derivative of this, we get e to the y. Take the y derivative of that next term, we get just x to the negative 2. And one last fourth mixing and matching, the y derivative of the first y derivative. There's that first y derivative again. E to the y plus x to the minus 1. And we just need to be careful again with our variables. Y is the variable we're differentiating. X is a multiplier for that first one. And then this term has no y's at all, so it's just plus 0, or it disappears. And so we end up with x times e to the y. So in some sense, that's just a procedural calculation. We'll talk about interpretation a little later, but when we talk about second derivatives, we just take one derivative and then take another derivative. Now there is one interesting feature that comes out of this though, and that's this mixed partial derivative. When we look at the x and y, or y and x, notice that the result we got was the same. It didn't seem to matter whether we took the x derivative first and the y derivative, or the y derivative first and the x. And we're a little bit interested in investigating whether that's true in general. Let's flip to the next page and see, for a different function, sine of x squared y, whether we get a similar kind of result. So we're going to take the partial derivative with respect to x and y, and that'll be the x derivative last, the y derivative first. And if we take the y derivative of this, we'll copy the x derivative. That we're just going to keep around for later. But we're going to multiply by the y derivative of this. Well, derivative of sine is cosine, and it'll keep the same interior, x squared y. And the chain rule says take the x, we're taking the y derivative here, you have to be careful again. The y derivative of that interior is just x squared times 1, or just x squared. And then we follow up by taking the x derivative of this entire expression. That's a little nastier because we need the product rule. We have x's in both terms. So we'll need the product rule here. That'll mean we'll need more space, so I'll bring this down a line. And we just go through it step by step though. The derivative of cos anything is negative sine of the same thing times the chain rule. Derivative of that will be 2xy if we're taking the x derivative, times the second, which is x squared, plus the original term, cos of x squared y, times the derivative with respect to x of the x squared, that's 2x's. Let's tidy that up just a hair. We'll have negative 2 x cubed y times sine of x squared y plus 2x cos of x squared y. That is what it is. Now let's contrast that with the second partial derivative with y then x in this order, which we interpreted as the y derivative last and the x derivative first. X derivative first. And so we're going to copy again the y derivative. We'll do that later. Our emphasis right now is going to be on the x derivative of the original function up here. We'll do that in one line. So the derivative of sine is cos. Keep the interior the same. And then take the x derivative of that. That'll give us 2xy's. Now again, we're going to have a product rule. When we take the y derivative, because there's a y in both terms, but we can handle that. Take the derivative of cos anything, we're going to get negative sine of the same thing times the y partial derivative of the inside. That will be 1 times x squared times what we had already there, 2xy, plus the original term, the original first term, cos x squared y times the y derivative of the second term. That'll just be 2x. Oh, lo and behold, even with this complicated example, notice what we end up with. 2x cos of x squared y. And over here, if we agglomerate all the terms, we end up with 2x cubed times 1y sine of x squared y. And we see these are in fact the same. So in two different examples, what we have encountered is that when we take the mixed partial derivative, x and y of the function, regardless of the order that we take those derivatives in, we end up with the same formula. Well, this is not just a casual occurrence. In fact, this is true for any of the reasonable functions that we can imagine. These derivatives are going to be equal to each other no matter what. Now, this may not seem too exciting, but what we just did is cut our workload down by one more derivative we don't have to calculate, because if we talk about the mixed partial derivative, we only have to calculate it once. It'll always equal the other version if we wanted to compute that, but we don't ever have to do that explicitly anymore. This is also true even for higher derivatives. We haven't talked about them yet, but we could imagine taking third derivatives and fourth derivatives as we've done earlier in the course. When we do that, it's only the variables that matter, not the actual order that those derivatives are taken in. So that's a nice reassurance that we can focus on the variables and not worry about which order we take the derivatives in.